Friends, good morning. Last day I sent you a long video. I know that. So today we are going to do a short video which will explain you the stereochemical aspects of a SN1 and SN2 reaction. Okay, let us go through that. So in order to understand this stereochemical aspects, we have to go through some physical things. Okay, physics. Ready? So here there are plane polarized. We are looking at plane polarized light. A plane polarized light is getting from an ordinary light. Okay. See, for ordinary light, you can see all direction vibration is there. So when it is passing through a Nicol prism, the Nicol prism or this polarization filter is called a Nicol prism. It has the capacity to pass only one type of vibration through it. So only one type of vibration will pass through it, and we will get a polarized or plain polarized light we will get at the end. Okay. Look, here we have a source, ordinary light source is there, and that light is passing through the polarizer, that is our Nicol prism, and then we will get a plain polarized light which is having vibration in only one direction. And when you pass this through a glass tube, okay, when a plain polarized light is passing through a glass tube which contain a substance, okay, so this particular substance, if it is optically active, then what will happen? This plain polarized light, when you pass through this substance, it will rotate the plane of the polarized light through a small angle. Okay, so that is called optical activity. Then we can tell this particular substance is having optical activity. What is that? Optical activity is the ability of a substance to rotate the plane of the polarized light, either to the left or right through a small angle. Okay, that is called optical activity. Okay. Now, next we can see what is optically active compound. Already we discussed the substance. Here itself we discussed the substance which can rotate the plane of the polarized light to either left or right through a small angle. That is called a what? Optically active compound. And what is polarimeter? And this is an instrument which can measure the angle through which the plane polarized light is rotated. That is called a polarimeter. Now let us see the rotation, how the rotation will be. Suppose this is a plane of the polarized light before, and if the plane polarized light, if the plane polarized light is passing through the substance, if the substance is rotating the plane of the polarized light to the right, then it is called a dextrorotatory. Okay, if the plane of the while passing the polarized light to a particular substance, if the substance is rotating the plane of the polarized light to the right, then that particular substance is called a dextrorotatory and or deform, and it is indicated using a plus sign. Okay, if the substance is rotating the plane of the polarized light to the left, then it is called a levorotatory or L form, and it is indicated using the sign negative. Okay. Now, what are the conditions needed for optical activity? We know that some compound is having optical activity. So what will be the condition to form optical active compound? What are the conditions needed for that? So the molecule must be asymmetric and there will be non-superimposability of mirror images. Let us see each one. So what do you mean by asymmetric molecule? Look at this molecule. In this molecule, the carbon is surrounded by 4 different groups. Then this carbon is called a stereocenter. But it is called, this carbon is called a stereocenter because, or it is called an asymmetric carbon because it is surrounded by all different 4 different groups. Okay, suppose if it is surrounded by same group, like in the case of methane, it is surrounded with the same group, then it is not what asymmetric, it is called a symmetric because the electron density is evenly distributed around the carbon atom. Okay, so the carbon must contain 4 different groups, then only it is called an asymmetric center or a stereo center. Okay. Now, What is a symmetric carbon atom? The carbon contains 4 different atoms and no symmetric distribution of electrons should be there. Okay. And now let us see non-superimposability of mirror image or chirality. Look at your left and right hand. One hand is its mirror image of the other hand, right? Left hand is mirror image of right hand. Now you place one over other. They are not superimposable. Each finger is upon a different finger, right? When you keep one on other, okay? But it is looking like it is superimposable, but they are not superimposable. So that is called a chiral object. If they are, look at the flask. Here, when you keep one flask on the mirror image, it is completely superimposable, and that substance is called a chiral object. Okay. Yes. Now, so already we learned what is chirality, the object which are not superimposable on their mirror image, that is called a chiral substance, and this property is known as chirality. And chiral means the object which are superimposable. Superimposable, just like conical flask on their mirror image, and they are called chiral. Okay, they are optically inactive. This type of molecule which are chiral are optically inactive, and those type of molecule which are non-superimposable on their mirror image, they are optically active. Okay, so chirality, optically active. Chiral means optically inactive. Look at this. If you take a molecule, okay, and if you see the mirror image, this is the mirror image. If you see the mirror image, this is its mirror image. Okay, this is attached with 4 different groups, right? So you are attaching, so there is a mirror, and when you keep one over the other, okay, when you keep one over the other, what will happen? They are not superimposing each other. Okay, A and B cannot superimpose. They are not superimposable on their mirror images. So they are not the same molecule. Understand? They are not same molecule. Now, next example, look at this particular example. In this particular example, you already know that what is a chirals, what is a asymmetric carbon, right? So look at this carbon, it is not asymmetric because each CH3 group, 2 CH3 group is attached, same group is attached. 4 must be different groups. So this is actually not going to be optically active. So propan-2-ol if you take, and its mirror image if you take, and if you are keeping them together, the CH3 will come, right? It is superimposing. 2 CH3 will superimpose on this, okay? And not only that, there is one more thing to understand whether it is optically active or not. Now the resulting molecule, so if you take the mirror image and if the resulting molecule is flipping to 180 degree, if you are going to get a same molecule, exactly the same molecule like A, the previous one, then it is not optically active or not superimposable mirror image. We can tell that they are they are superimposable mirror image. They are not non-superimposable mirror images. Okay, C is superimposable on A. Okay, C is actually superimposable on A. So because of that, they are chiral molecule. Okay. So what I said, again, I'm repeating. If you take this, first you check whether it is asymmetric or not. It is not asymmetric. You rotate it, you take the mirror image, and after that you rotate it to 180 degree. See whether A and C are mirror images. If they are not mirror, if they are, sorry, see if A and C are superimposable. If they are superimposable, the molecule will be chiral, okay, and they are not optically active. Clear? Now, next case, next example, let us take this example. This example is also, our first thing is we have to find first there is a chiral center or not, or asymmetric center or not, we have to see. Look at this carbon atom is surrounded with the 4 different groups, so it is asymmetric. Now you are taking the mirror image, and that mirror image now rotate to 180 degree. So what happens, see at C2H5 here, This is the F. Now you keep F over D. So C2H5 will be superimposed with the CH3. Means different groups are coming down, right? CH3 with the C2H5, OH with OH, and H with the H. Okay, so they are not actually superimposable mirror images. Okay, they are not actually superimposable mirror images. Because of that, this is optically active. Okay, this is optically active, and they are non-superimposable. So two reasons are satisfied here. One is asymmetric center is there, and the second one is they are non-superimposable mirror images. Non-superimposable mirror. Because of these two reasons, this is optically active. Okay. Next. Look at this example easily, how easily we can find out one is superimposable to its mirror image or not. First, you have to take, this is one molecule. Now you take the mirror image. After that, you rotate it to 180 degree and see the first and the final molecule are superimposable. Okay. So they are not superimposable here. Okay. So they cannot be superimposable. You can understand from here, this picture and this picture. If you keep this over this, Br and Cl will come together. Cl and Br will come together here. Okay. And because of that, they are not superimposable mirror images. So they are optically active and it is having a symmetric center also. Okay. Now in this particular case, see, two same atoms. So from here itself, we can understand they are not they are not optically active because it is not having an asymmetric center. Now you are taking the mirror image. After that, you rotate it to 180 degree. And when you keep one over the other, all the atom will superimpose. Here, you know that H and F is going to superimpose, but doesn't matter. The other atoms are not superimposing. Okay. So if all the atoms are superimposable, then only we can tell they are superimposable to its mirror image. So in this case, all the atoms are superimposable to its mirror image, so that it is a chiral. Okay, it is not optically active. Now let us see what is enantiomer. The stereoisomer related to each other as non-superimposable mirror images. We have seen here. These are related to each other as non-superimposable mirror images that are called enantiomers. Okay. So how enantiomers are different? Actually, enantiomers, they have the same molecular formula, same physical properties, melting point, boiling point, refractive index, etc. But they differ only in one thing. They will rotate the plane polarized light in different direction. Okay, that is the only difference between enantiomers. Okay, they will rotate the plane of the polarized light to different directions. Okay, left to right. If one is rotating to left, the other will be rotating to the right side. By the angle of rotation will be the same. Okay. Now, what is racemic mixture? A mixture containing two enantiomers, 50% deform and 50% L form. Means 50% dextrorotatory and 50% levorotatory is there. Then that one is called that type of mixture is called a racemic mixture. They are optically inactive. Why? Because 50% is levorotatory, means 50% is rotating the plane of the polarized light to the left. So the other 50% will rotate the plane of the polarized light to the right. So equal angle it will rotate. So it will finally the direction will never change. If you see the direction of plane polarized light, whether it is changed or not, it won't change because 50% is levorotatory. So the rotation of levorotatory substance will cancelled by dextrorotatory. Okay, that is the reason. As the rotation due to one isomer will be cancelled by the rotation due to the other isomer. This is the reason. Okay. A racemic mixture is represented by plus minus. Plus minus indicate that both in a 50-50%. Okay. Now, what is retention? Retention of configuration is a preservation of the spatial arrangement of bond, okay, to an asymmetric center during a chemical reaction, okay. So how we can preserve the configuration? No bond to the stereo center is broken. The product will have the same configuration. Now let us see retention. In this particular case, see here, who is coming? In this particular case, Y is added here, okay. So this is the molecule, this is our reactant. So X has gone and Y is added here. Here you see X has gone and Y is added. So if you look at these two examples, you can see that here Y is added on the same position of X. So it retain its configuration. There is no change in the, only one change is the atom changed, the structure being the same. So there is no change in the configuration here. But here you see what happened. The X is not added on the same direction. It is added on the place opposite to the direction of X. This is X, right? So opposite direction. So this side only the Y is added. Opposite direction of X, Y is added. So that is called an inversion of configuration. Okay. If it is on the same side, that is called a retention of configuration. If it is on the opposite side, then it is called a retention of configuration. Okay. What is happening here? -2-methyl butane 1-ol. When it is reacting with the HCl, okay, it is going to react with the HCl. So OH will break and go in the direction Cl will come, okay. So here there is a retention of configuration. The sign is different, that doesn't matter. The configuration is same. Even a substance with the same configuration may have different rotation, okay. That is why the sign is different, okay. But the configuration is not changing because the same direction only the Cl is attaching, okay. That's the reason, okay. So this is what explaining here. So inversion in configuration means the configuration is changing during a reaction. This is the example. Look at this example. Here what happened? Here SH minus is coming and Cl minus is leaving. Okay. So SH minus is coming from a direction opposite to the direction leaving group. Okay. Why? Because if it is going through the same direction, there will be hindrance because this is also negative, this is also negative, so there will be repulsion. So it is coming from a direction opposite to that. So we will get a configuration. The same chiral center is saved here, and we will get the same configuration. We will get a inverse configuration because the side in which SH attached is opposite to the CCl bond. Okay. So this is called inversion in configuration. Racemization means if 50-50% mixture of both the isomer is obtained. Already we discussed. So that is called a racemization. Okay, now let us see the stereochemical aspects of SN2 and SN1 reaction. In case of optically active alkyl halide, the product formed as a result of SN2 mechanism has the inverted configuration. What is the reason for that? That also we explained. Why? Because already I explained to you, that is this Br, the leaving group is negative and the coming OH minus group is also negative. Both of them are coming from the same direction, there will be repulsion. So OH will be coming from maximum distance from the leaving group, that is opposite direction of Br. So this will result in the inversion of configuration. Looking at this, you can tell that the beta OH is added on opposite side of Br, so it is inversion of configuration. Okay. And now let us see SN1 mechanism. In case of optically active alkyl halide, XN1 reaction is complete by racemization. Very important. By racemization, we already know this is an example for SN1 reaction. In this case, look at this case, we can see that this is two-step mechanism. First, yesterday we discussed, right? First, this bond is breaking and it is forming a carbocation. Now look at the hybridization, 1, 2, 3 bonds. So sp2 hybridization, and its shape will be trigonal planar shape. The central carbon is having, C plus is having a trigonal planar shape. Okay. Since the shape of the central carbon atom is planar, trigonal planar, so it will be like this, trigonal planar, what will happen? Since it is planar, the incoming OH minus will be coming. There is equal possibility to come from this side and the opposite side. Okay, so 50% will be coming from this side, so that will result in retention of configuration, and 50% will be coming from this side. Those that will result in a inversion also. Or you will get 50% of each configuration. So that will result in racemization. Understand? Both the configuration we will get 50% because equal possibility of attack from this side and that side, because the carbocation formed is planar. That is the reason. Now let us have a look at all these things. Let us see inversion, retention, and racemization together. So if this is a substrate, okay, this is a reactant. If a Y is coming, this is here Y is coming. That is, the Y is attached in the direction opposite to X. So this is what inversion of configuration. But here see Y is on the same place of X. So this is retention of configuration. If you are mixing, if you are getting a mixture of A and B, that is retention and inversion, 50% we are getting. So that compound, we can see that is optically inactive because of racemization. Understand? That's all. That's all for today. Now let us discuss the lesson in next class.